example for us. Let's say we have a bag of M&Ms, and we have 9 brown, and we have 6 yellow, and let's say we have 7 red, we have 4 orange. What else is there? 2 blue. I don't know, 2 green. And we want to determine, number 1, the probability for a yellow. Number 2, the probability for a blue. And let's think about the probability, these two probabilities, and compare. So in this bag, I know I have these M&Ms, and without looking in the bag, I reach in and I want to know what is the probability of selecting a yellow without looking. Then I want to determine the probability of selecting a blue without looking. What do I have to do first?
The yellow back into the bag?
I'm sorry?
After you return the yellow back into the bag, or do you take the yellow out if you pull it out?
Very good question.
With replacement or not with replacement?
Very good. Very good question. Good point. So let's do it with replacement first. Excellent. You anticipated where I was going. Awesome. So, what is the first thing we need to perform? What do I need to find?
The total.
The total. First, I need to find the total. So, here's how I'd like to do the total. 9 plus 4 is 10. I'm sorry, I meant to 6 plus 4 is 10. And then 7, so this is 21, and then that must be 30. So this was a 10, this is an 11, and then plus 9. So the total is 30. So what is the probability if we, this is valid for the second one, there is no need for the first one, but what is the probability of selecting a yellow?
20%.
So the probability of selecting a yellow is the number of yellows in the box divided by 30, which indeed simplifies to 1 divided by 5, which indeed simplifies to 0.2, which indeed simplifies to 20%. Awesome. So the number of outcomes, possible outcomes, 6. Total number of candy in the box, in the bag, 30. 6 divided by 30 simplified by 6 will give us 1 over 5, or 0.2, or 20%. Excellent. Assuming now we are not eating the yellow candy or the yellow M&M and we put it back, what will be the probability of selecting a blue without looking? First, I need the fraction for everyone to see.
2 divided by 30.
2 divided by 30, we simplify by 2 and we get 1 over 15. And we change that into decimals. And then
0.067.
0.067.
6.7%. Or, yeah.
Something. So 1 divided.
0.067. My bad.
No worries, no worries. So I'm going to put the point in front. That's how lazy people do it. So 6.7%. Very good. So by comparison, what will you say? And then we're going to look at the other one without replacement. So by comparison, right? What will you say? Roughly about 33 times as much, right? 6 versus 21, 7 versus 21, about 3 times as much, right? That's what I wanted by comparison, right? So the probability of selecting a yellow is about 3 times as much as the probability of selecting a blue. But now, let's say without replacement. So the first one doesn't change. No question there. But what about the without replacement? So I take the yellow, I selected a yellow, let's say, I ate it. I didn't put it back in the bag. What is the probability of selecting a blue now? As a fraction first.
29.
So I still have the blue, I still have 2. But now how many candies are left? How many M&Ms are left in the bag?
29.
29. So see what's happening here. And I am going to talk about it after we look at homework a little bit. So what happens is the fact that we did not put the yellow M&M back in the bag, that affected the probability of getting a blue. So 2 over 30 and 2 over 29, because I divide by a smaller number, this answer is bigger than that. So it influenced the fact that we took an M&M from the bag and we didn't replace it. It had an influence. This is conditioned on what happened on the first trial, because now the probability changed. And 2 divided by 29 is roughly 6.9%. Good. So now I'm ready to look at and share the screen. Where is my, okay, here it is. I don't want this. I want this, and I want this. So let's take a look. What are our preferences on this? Wow, 20 questions. Good. I'm ready. And I'm on page 5.
Yes, Jenny.
Let's start with number 8. Good. 8, okay. Is the following a probability model? What do we call the outcome yellow? Okay, let's start with that question. What do we call the outcome yellow?
Possible.
Impossible event. Awesome. Okay. Now, question. Is this a probability model or probability distribution also called? Anyone?
A.
They do not add up to 1?
Yeah.
So we have 0.3, then plus what is that, 60, and then plus 0.15. Very good. They do not add up to 1. Well done. Continue. What do we call? You already said the impossible event. Good. Well done.
Can we do question 13?
Yes, did you say 8 or 9? Now I'm confused.
I said 13.
No, before that.
Oh. I don't know. I didn't get a question before.
You did 8. You did 8.
Okay. So did you ask for 8 or for 9?
No, just 8.
Okay. Just making sure. Good. Let's look at 13. Use the spinner shown to answer the question. Fine. As soon as it is equally, this is a key. These are key words. equally probable. So every event, 1, 2, 3, 4, 5, 6, 7, 8. So we see 2 yellow, 2 red, 2 green, 2 blue. So all these colors are equally likely. They have equal probabilities of occurrence. The pointer will land on any of those colored regions. Fine. If the pointer lands on a borderline, spin again. Fine. If the spinner is spun once, find the probability that the pointer lands in a blue region. So remember what we said. I'm going to stop sharing so I can show. So the probability for blue is the outcomes, all the blues, right, divided by total. How many are total? How many are blue? Who knows what I'm writing? How many blues?
2.
2. How many total sectors, circular sectors?
Wasn't it 8?
Good. So this is 1/4, which is 25%, right? It's a quarter, which is 25%. So I don't know what they want, in which form. So let me share my screen again. Okay. So
They want it as a fraction.
okay, type an integer or a simplified fraction. Perfect. So they want this 1, what is my keyboard? 1 divided by 4. Good. Anything else we want to look at here? What if we look at this one? Let's say, what is this? 14. Okay. A single die is rolled twice. The 36 equally likely, keywords, equally likely, they all have the same probability, are shown here. In other words, if there are 36, the 1, 1 will appear 1/36. The 1, 2, or 2, 1, if we want to look at the sum, this will appear twice out of 36. Who knows what they're asking? So find, here it is, the question. Find the probability of getting 2 numbers whose sum is 8. So I'm going to stop for a second. So the probability for a sum equals 8. So out of the total, which we know is 36, we have the number of outcomes with sum 8, and we'll see how many. So we go back. Okay, sum of 8. 6 and 2, 5 and 3, 4 and 4, 3 and 5, 2 and 6. So as you see, there are 5 for sum of 8. So then we go back, and this is 5. 5 divided by 36. I got 0.13888. Now let's see what they want. They either want the fraction or something decimal or 13.89%. I'm not sure. I didn't read far enough. Okay. The probability of getting 2 numbers whose sum is 8 is, type an integer or a simplified fraction. So in that case, I will enter 5/36. 5 and then 36. Good. Other questions? Anything else here? Do we want to look at anything else?
20.
You said 20?
Yeah.
Okay. The theoretical probability of a coin landing heads up is 1/2, as we discussed. Does this probably mean that if a coin is flipped 2 times, one flip will land heads up? No, that doesn't mean that. If not, what does it mean? That if a coin is flipped 2 times. Okay, so this is theoretical or classical, same thing. Theoretical and classical mean the same thing. So we're not conducting the experiment. We know that if it's a fair coin, then half and half, 50%, 50%. Okay. So, yes, it means that if a coin was flipped 2 times exactly, one of the tosses would land heads up. No. Heads up, no. It means that if a coin was flipped many times, at most 1/2 of the tosses would land yes, but I will not select before I read the other two. Yes, that's what it means. No, it means that if a coin was flipped many times, at most 1/2 of the tosses. So let's read. No, it means that if a coin was flipped many times, about 1/2 of the tosses. Yes, about. Yeah, not at most. Careful. I was wrong. Not at most. About. This is better. Yes, it means that if a coin was flipped 2 times, at least one of the tosses. No. So does this probably mean that if a coin is flipped 2 times, one flip will land head? No. It means that if a coin was flipped many times, about 1/2 of the tosses would land heads up. And the coin was flipped 2 times, he said no. English language has a lot of nuances. That's why I'm trying to read as careful as possible, just to make sure that, see, this was a matter of at most and about. So that it hinged upon just basically not on math, but it hinged upon these 2 words, at most and about, which has nothing to do with math, but okay, I don't want to try again. I think I should have clicked on something else. Very good pick. Very good pick. Anything else?